I'm Bob Terry. I'm a lifetime and founding member of the Mars Society, plasma scientist by profession, and now a sort of independent researcher. And one of my hobbies is fusion schemes. And one of my favorite fusion schemes is the Polywell and things I would like to do with it, which I'll maybe tell you about in a couple of years to make it much better. But what I want to do now is to reprise a review I did for the Baltimore Science Fiction Society with a little bit of a spin more toward how such a fusion device as a Polywell might be applied in space travel. You know, the space travel is a little different application than a power reactor. So there's some considerations that are of interest there. The Polywell is a contraption which is sort of pictured here. This is one due to Young Park. This is a modern Polywell. It has 6 circular magnetic coils. They are positioned on the opposing faces of a cube, and within the cube is produced a magnetic well, hence the name Polywell. All the magnetic fields point inward in this application for making a reactor. All the fields point inward, and the magnetic field lines try to squeeze out around the coils. And we'll see, look in detail at the field patterns and why they're useful, and the good points and bad points about them. And so this is the configuration if you imagine cramming all this plasma together and making a fusion reactor. In the case of making a fusion rocket, what you would do is basically flip the direction of one coil only, whereupon the magnetic field would come out that direction and all the other fields would form into it. And you could put further coils out, stay out in the space above to form a little bit of a nozzle. All the magnetic fields would ultimately loop around on themselves because the magnetic fields always close on themselves. And you would have yourself a little plasma rocket. Now, the question is, would it work any better than the fusion reactor? And of course, that's the name of the game. Because it's a little easier to make it work better than the fusion reactor, but it's not guaranteed at all. And let's see. Well, it doesn't want to advance. Does this want to advance? It did before. This is fascinating, isn't it? I've never seen this application do that. No. The window is moved over because they have to move it off screen. Any idea? Well, it was moved off to the, yeah, okay. Oh, okay, well that's, thank you so much. I'm sorry for the blunder there. I don't know what did it. Anyway, so as an outline, why is fusion energy of interest? We all have our opinions, and there are some facts that are relevant here. What's distinct about the Polywell? How does it arise as a device? How does it approach the task of fusion energy? Where are the active programs and the central technical issues, and how is the research progressing? That's more or less, an outline of what I'm up to. Now, let's see. We're going, okay. What motivates this quest? Well, the first point here, look at the night map. The backgrounds of these slides used to be a nighttime map of the planet, but been given this room and the darkness, and I didn't want a dark background, so I removed it. But if you've ever seen the nighttime map of Earth, the only place that isn't ablaze with light is North Korea. And so if you ask yourself, why would we care about all this fusion? And we know how many quads of energy we dump into making electricity for our grid. There's no better lesson than the nighttime view of Earth to understand why we want fusion energy for all our industrial applications with electricity. Now, one of the common ways of doing that is hydrogen and deuterium and tritium, and here's one deuterium-tritium fusion channel is a commonly examined fusion channel. The compact energy sources that we have really have relatively limited kilowatt hours per kilogram, and kilowatt hours is 3.6 megajoules of energy. So in terms of megajoules or kilowatt hours per kilogram, fossil fuels bounded above by about 14. It's the best you ever get, no matter what you do with a fossil fuel, and including hydrogen, oxygen, rocket fuels, and things like this. You basically don't get much more than about 14 kilowatt hours per kilogram. Now with fission fuel, U-235, you get 2.25 times 10 to the 7th kilowatt hours per kilogram. All right, and the disparity between, and then with fusion fuels, you go from 2 to 9. So P-boron 11 is a very popular exotic fusion fuel cycle. This is attractive to a lot of people because it spews no neutrons. And so you don't like the notion of having deuterium tritium in your tokamak, activating all your magnets, making you take the thing apart every 10 years and roll this highly excited iron out to the dump and dumping it, right? If you don't want to do that, you might think, I want to use P-boron 11, I will not have a single neutron. Life is good. Well, what is not often mentioned is that in P-boron 11, there's a gamma ray channel. It's 1 part in 1,000. All right, so if you're just looking at P-boron 11 in the laboratory doing some tests, your gamma ray is about 100 MeV gamma ray, the real nasty rascal. So in the laboratory and making tests, if you ever got P-boron 11 to ignite, you wouldn't care, because only 1 part in 2,000 is this gamma ray. But if you ever have a serious fusion reactor that's at break even, running P-boron 11, don't stand next to it, because that gamma ray will eat you alive. You want that fusion reactor, put behind a nice little water screen so that gamma ray will Cherenkov itself into oblivion, and light up the room for you a little bit with some indirect Cherenkov light. You can probably read your newspaper by it. But you do not want to stand next to that operating P-boron 11 reactor. A similar thing would apply now in deuterium tritium. Basically, you're pulling out this channel a lot. You get a neutron and 14 MeV of free energy, and 3.5 MeV over here. So you have helium-4 coming out and a neutron. In deuterium tritium, this little rascal neutron is the only thing that makes it not so green. But they're mostly green, mostly fusion reactor, mostly green, mostly clean. They're very compact. And NASA just knows that this is a solution to the best possible space travel. They know it in their bones. They know it. They're so keen on it that you will find charts at NASA that sit there and draw timelines of technology, and they will fancifully, I say fancifully because I don't know how they think they know this, they will put a date certain when fusion rockets are going to be available. In the 2030s sometime. Fusion is the future and always will be, as it were. So anyway, but these very high specific energy yields are what make these fuels so interesting. I mean, this is basically you imagine 1/2000th of all the world's water, and you start burning at these kinds of yields, you basically don't have an energy problem, perhaps for the foreseeable lifetime of the human race. And certainly if you bring in water from other sources, it's even better. Mars, asteroids, comets, whatever, plenty of stuff. So now what is the interesting thing about fusion? How does it actually work? The notion of scientific break-even is embedded in this constraint: the density and the temperature in electron volts, and the confinement time in seconds, density in inverse cubic meters. If you can get this trio of numbers to exceed that limit, then you have gone over sort of generalized Lawson criterion. And in a steady state system, that steady state system is now producing more fusion energy, or about equal fusion energy to the energy required to confine that volume of material. And so that can operate steady state, producing energy until the sun don't shine, as it were, and nothing changes. That's a steady state solution. Yeah, of course. You keep adding fuel, but as long as you're burning it, that's a steady state solution. You bring the fuel in, take the ash out, let the energy come out. Whatever you're going to do, that's a steady state. Most fusion reactors don't go there because most fusion reactors don't work yet. And even the ones that are proposed to work don't think they're going to go there. Most of them tend to think they're going to be pulsed in some way. But the Lawson criterion you hear about is based, in all these fuels. These are the peak temperatures of the cross section. Now, see, P-boron-11 is really fierce. You have to drive this really hard because you have to strip all the electrons off your boron. And that's a lot of work. So P-boron-11 is a very aggressive fuel if you can get things that hot. You have to look at 120 kilovolts. You have to peel the energy off these guys. And so it's tough, but it's interesting. But the Lawson criterion, or that kind of criterion, actually comes from the peak of this rate coefficient curve. And this is logarithmic in temperature, billions of Kelvin, millions of Kelvin. These are actually the same scale. If you just throw the power of 3 over there. The author of these graphs just, was billions, billions. Pretty soon you're thinking about real money. I was thinking of Everett Dirksen's quote or something, perhaps. I don't know. But so they're the same scale. But the upshot is, with temperature, the cross sections rise rather abruptly, but it's still to get to the Lawson criterion, you're at the peak of these yield curves, and deuterium is a little further afield over here. So, and then as you look at the criterion in tau and E, the minimum is there for deuterium and there for deuterium tritium and deuterium helium-3. This is a famous helium-3 that the Chinese might find on the moon but cannot use because they don't have a fusion reactor either and not likely to get one. Helium-3 is a tougher problem of fusion than deuterium tritium, but not as bad as deuterium deuterium, and certainly not as bad as P-boron-11. But so deuterium helium-3 is, you could use that helium-3 from the moon if you could get there, but first you have to build a deuterium tritium reactor, okay? And that's not so easy. But on the other hand, the rocket problem is easier. In the rocket problem, I don't have to have break even. In the rocket problem, I can climb up that rate coefficient and never get to a Lawson criterion. But if I am pumping out more fusion energy because of the great yield of the fusion reaction, I will have the only plasma rocket that has ever been exothermic. The only plasma rocket that has ever actually had a fuel that it burns. All other plasma rockets make you take all the energy you want to put in the working fluid and add that energy to the working fluid by external heating. That's why plasma rockets like Vasimir and even ion propulsion engines are so pitiful in terms of thrust. You have to find that energy, and then you have to couple it into the material with high efficiency, and then you have to throw it out the tailpipe. And you don't carry any, there's no fuel value in the working fluid. But with a fusion rocket, there is fuel value in the working fluid, extremely high fuel value in the working fluid, like no other working fluid we've ever seen. So the fusion reactor, if you look at the thrust efficiency of a rocket, this is the speed of the flow that you're producing. This is the speed of the rocket. This is just how sort of the efficiency of thrust power. The fusion rocket has energy to be released. So if I go back to the table I had, 9.5 10 to the 7th was kind of the middle range of the fusion channels. I'll convert that to megajoules. I've got 342 terajoules per kilogram full burn. That is a tremendous amount of energy to put in any working fluid. I can even lean that out by a factor of 1,000 and still exceed the hydrocarbon thrust power by a factor of 6,800. All right, so that's where I am. I've got 7 orders of magnitude improvement in the specific energy of the fuel that I can release. All I have to do is figure out how to tickle it. Little problem. But it's kind of like, a diesel engine. I mean, you take the diesel fuel mixture, you compress it, and it automatically ignites, and you pull the energy out. And so the fusion is similar to that, except it only has one component. Well, maybe two if it's deuterium tritium. It's kind of like diesel and oxygen. You compress the fuel enough, hard enough, fast enough, bring the temperature up, and as you climb that curve, you're going to maybe get 1,000th of the release of the potential energy in that fuel. But that part in 1,000 or even part in 10,000 is significant in terms of rocketry. So all you really have to do is beat the energy that it requires to climb the curve a little bit, and then you're getting more energy out compared to all your confinement energy. You're going to dissipate energy making the confinement in the rocket, but you're still perhaps going to get energy out in copious amounts. Well, that's the theory. Now, if we look across the universe and we ask, how does fusion happen? Everything about fusion happens because there is divergence not equal to zero somewhere, okay? Every vector field, as most of you probably know, has a bristly part, the divergence, and a rotation curly part, the curl, all right? The curl of the vector field compresses nothing. The divergence compresses, and if fusion is requiring compression, you must have some kind of field like gravitational. Certainly del dot G is not zero in a star. Inertial confinement, your average fusion bomb, this flow field is converging because of various influences on it, and so that's not zero. In a Polywell, we're trying to exploit electrostatic confinement. Del dot D is certainly not zero. We're going to put a charge in the center of that well and suck it in and make it crack, all right? Now, most of all other confinement schemes use magnetic fields, and until somebody shows me a bag of monopoles, del dot B is always zero everywhere for all time. So the magnetic field can never itself provide compression. Not directly. The magnetic field has to provide compression by sort of, sloughing it into a package, and that's what the Polywell does. The Polywell arranges a compression that sloughs things into a package. Well, the single greatest failure of American physics, or maybe American and European physics in the 20th century, is a failure of controlled fusion. I mean, that's just a fact as far as I'm concerned. This entire zoo has been going on since the end of World War II, and in only a few cases are any of these things credibly on the path to break even. The National Ignition Facility, I have a really nasty name for that thing, but the National Ignition Facility, being generous, recently had a tour de force. They had a pardon my French, Donald Trump style tour about break even. And they published a paper in Physics of Plasmas. They came around and talked to us about all this, and we got them to the Philosophical Society of Washington, just over there. And we asked them, what do you mean by break even? We mean, we got it in a little package, and inside that little package, it was exothermic. And they did a great job. I will not fault the experimentalists at Livermore. They nailed that experiment dead to rights. And they demonstrated exothermicity in a small package. Okay, so how far are you from engineering break-even? Factor of 10 to 50,000. How far are you from scientific break-even? How far are you from scientific break-even? Oh, about a factor of 10,000 or so. So that's the same idea as what you might find in a rocket situation, fusion rocket situation. You'll drive it up and get a little bit of yield from the fusion reaction, but you're way, way below break-even. But this is exothermicity, could be measured. They're very pleased with it. The Polywell sits in this line of development. It starts with inertial electrostatic confinement. Remember Philo T. Farnsworth? Only fans really remember Philo. He invented television before it got ripped off by Sarnoff. Yeah, and so Philo T. Farnsworth invented also a little thing called the Farnsworth fusor. And the Farnsworth fusor was trying to say, if I want some ions to crack into themselves and fuse, I'll put a grid here and I'll suck the ions in and I'll throw some electrons into the center and the ions. So he used a physical grid. And it actually worked, and you could maybe measure some fusion events, and that was the path to there's now the path to the fusor, and that was the path to the Polywell. The difference between the Polywell and the fusor I'll illustrate in a moment. It's a matter of how do you save those grids from being eroded by that nasty plasma, because plasma likes to chew up stuff really well. Now, in terms of magnetic confinement, the path that has shown us nothing so far, ITER is not, it's on the path to some kind of break even, they think, but it's going to be a huge, huge device. And ITER, as I often call ITER, it mostly eats money now, but it's good at that, and it's a really great device. All these things have taught us more physics, more physics that has not quite gelled into something we'd call a technology than almost any other field of classical science since Maxwell. I mean, this is a huge zoo of wonderful physics, just extremely exquisite mathematics and experiment and all manner of stuff has been learned here, except how to make fusion happen. However, so there's a transition between a fusor. This is kind of the Farnsworth fusor. You have this little grid in here, and you pull a positive charge on this, and it pushes the ions away. But then you try to get the electrons to form up here in the center. So the ions fly past the grid into the negative voltage formed by here among these electrons. And you pull them all in here, and they all light up. The problem is you get any kind of energy density in here, you just chew this thing up. It just goes away. And here's another one operating in hydrogen, where it's got a little bit of a dense pile of plasma fold up in here. I mean, they're high school kids that build these things. Very interesting little experiments. Again, marvelous physics demonstrations and lessons in physics. And they're built by some high school kids, and they're working fine. Perhaps. I don't know. I mean, I'm not sure if they pulse it or whether they just have to have a big capacitor and let it bleed in. This doesn't necessarily have to draw a huge amount of power, but it will sooner or later chew up its grids. Now, the thing that made this from fusor to Polywell is due to Robert Bussard, who originally thought of this whole concept as a way to get fusion power for rocketry. And he sold this thing to the Navy and to Air Force as a concept of how to get fusion power for rocketry, because he recognized, as I said, that the rocket problem is a little easier problem than the stationary power reactor. It's a little easier to do. So why not try this? And so he invented the Polywell, and what he did was to add magnetic insulation. So we have now currents here which provide these magnetic fields and keep the electrons from essentially roasting this material and evaporating the grid. So if you have an electron population which you're trying to confine inside this magnetic well, now the electrons don't hit this tube because you've arranged the magnetic field in a pattern like this. So the electrons have to stay off these surfaces, and you can keep your magnetic coils from roasting. They mostly get cooled to try and chill off their internal heat. In the Polywell, like the one I showed you on the first slide, there's water flowing through that jacket, and the water is pulling the heat out of the magnets. But the magnet's surfaces are not much torn up or impinged on by the electron population, which you're trying to place down here, because you want an overcharge of electrons down here in the center, so it'll suck your ions in, warm things up, and produce a fusile situation. So that's basically what you're trying to do. Now, in terms of subtleties, these are the lines of vector potential. The isosurfaces of the vector potential contain the lines of B, RZ. So if I imagine a line of force, it stays on an isosurface. And that's partly why I plot it here, because it's easier to plot those isosurfaces. I'm just making a cut. They're essentially coil 1, coil 2, coil 3, coil 4. And if I did the whole problem, I'd have coil 5 on top and coil 6 below or something, so it would be that. I've just done essentially this is a map of the fields right through the center of that array. So it slices through the coils like 1, 2, 3, and 4. The coils here and here, top and bottom, they're balanced out. Their forces don't even show because they're balanced at the midplane. and they're repelling each other so their forces do not appear.
So the colors are not the coil?
No, the white spots, if you like, the white zones here in the center essentially form the boundaries of the coil.
Right, but the red and the blue are the same.
The red and yeah, this is essentially how the current goes out of the paper into the paper, out of the paper into the paper, out of the paper into the paper. So if you do your old right-hand rule, you'll notice that all the fields oppose each other, and then the directions of the fields. If this is in, they come in and they fly out. This field comes in and flies out. So you have surfaces here, and now I have three families of cusps. Along the axis of the coil is a familiar point cusp. And this point cusp was the thing that people exploited in magnetic mirrors for years and years and years at Livermore Laboratory and other places. They would try to hold the plasma in the magnetic mirror, and to the extent you have electrons or ions, which are relatively collisionless, when they roll along the field line and come to the throat of the mirror, they spin up. And so if you look at it, you're spinning fast, 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 and then you fly back out. It's partly the V cross B drift, but this is just basically circulation. This preserves magnetic moment because you have an energy relation between the kinetic energy of rotation and the kinetic energy along the magnetic field. And because the magnetic field can do no work, it's always perpendicular to the flow. It does no work. So as you spin this thing up, it has to get the energy from somewhere, and the translational energy stops, and then it flips back. So this mirror effect is a perfectly fine way to confine plasma, except that plasma always finds a way to kick itself out and leave the mirror. Okay, so that's what happened in the Polywell. There is a big fight going on between getting electrons to fall into this well and then getting electrons to leave along these cusps. There is a thing called, by Bussard, the funny cusp. I had no particular creative thing to call it, so it's been called the funny cusp ever since he named it that. And there are the point cusp, which is very, very easy to see. This is where there's a single line where the field comes in. But the line cusps are these zones in between where you have sheets of magnetic lines opposing each other. And they're sort of sitting along the edges of the cube. So they're line cusps. You can have, I'll show you a more regular line cusp in a simple calculation in a minute or two. So you can have these line cusps, and they will also reflect particles, except the particles are sort of running along in a sheet, and they're spinning up. They spin up too much, and they reflect back down. So the line cusp tends to have more losses than a point cusp, mostly because there's just more area for it to lose particles. The particles that come to the top of the cusp, if they haven't reflected and they get kicked out, get on the other side, now the field gradient goes the other way. Once they get past the peak of the cusp, it kicks them out. It's just like the cusp is trying in effect to exclude the plasma from that tight place where the field is strong, and it doesn't care. If the plasma goes past the peak, bye-bye. It shoots it that way. And there are a lot of other losses too. Now, the Polywell does not operate in a really hard vacuum. In fact, many of these things want to operate in relatively higher pressure. And so now the question is, why is this interesting from the stand? Okay, 5 minutes? Oh, goodness gracious. But there's no one following me.
I have to move the camera into another room.
Oh, that's okay. I can continue to talk, unless these people leave. All right, anyway. So, because I do have a few more things that you'll enjoy. So I'll try to wind it up real quick and then go back and fill in, okay? So the upshot is that there is a ratio of plasma pressure to magnetic pressure called beta. Very creative terminology here. So beta, yet another beta. And then Taylor in 65, that's how old all this stuff is. Taylor back in 65 showed that if you had this kind of gradient, this is a gradient perpendicular to the magnetic field, and you compare the dot product of that with the dot product of the field itself. If this is greater than 0, then this assembly is MHD stable. And MHD stable says that I've got these lines curving away from my plasma. If I try to put plasma in between the field lines, it's squeezed back out. Whereas if I have the field lines going the other way, then when the plasma goes out between them, it finds more space and the plasma leaves, and so the material can just sink down in the plasma. And so concave versus convex. The Polywell is the only fully convex magnetic confinement scheme. It has essentially convex fields hitting the plasma in all directions, okay? And so because of that, the 0th order, it's MHD stable, so you hope that you can sustain a high beta. In most things like a tokamak, you cannot sustain a very high beta because the thing will just tear up on you instantly. Well, this will tear up on you instantly. It's a matter of how fast the instant is. This one might have 10 times as long confinement time than the tokamak for the same kind of situation. But this kind of criterion still tells you how to assess that basic stability. So once the basic stability is there, Scott Cornish, these are recent experiments out of Australia. These are electron confinement measurements, and the red curves are the theory based on some straightforward, it doesn't look straightforward, but it is relatively straightforward, self-similar picture of how these electrons stay on the curves. So the notion of how the electrons stay in the well is pretty well obeying the theory of the situation. And so this is a recent result. A lot of people are bringing polywells online, and this is work by the Australian group that kind of verifies the fundamentals.